Hello. Let's learn about complex numbers. First, we need to start by talking about real numbers. What is a real number? Do you remember what a real number is? Take a moment to think. Can anyone come up with a definition of a real number? Well, a real number is any number that can fit on the number line. So let's draw a number line. And here we have a 0. Here we have 1, -1, pi is somewhere in here. There's a positive and there's a negative direction. Any number that fits here is a real number. However, sometimes when we're solving quadratic equations, which is what we've been talking about, you get numbers that are not real. Imagine the quadratic equation, x squared minus 4 equals 0. This you can solve with factoring, x minus 2x plus 2 equals 0, and you get x equals 2 or x equals minus 2. But what if you have x squared plus 4 equals 0? It's not a big change, just a minus to a plus, but then what happens? Well, you can analyze this equation graphically. Imagine the graph of y equals x squared plus 4. This is like a quadratic, but that's moved up 4, so you have the vertex here. Now imagine that y is equal to 0. Plug in 0 for y. And you get this equation. Well, what do you notice about when y is 0 for this quadratic? Doesn't have any x-intercepts. What does that mean? Does that mean this equation has no solutions? No, it just means it doesn't have any that are on the number line. So we can still do solving like so. Simply subtract 4 and do a square root of both sides. Okay. What is the square root of x squared? I'm cringing because I'm expecting someone to say it's x, but fortunately this is a recording, so I don't actually have to listen to that. The square root of x squared is not x. What is the square root of x squared really? Does anyone know? I don't know if anyone knows. The square root of x squared is absolute value of x. What is the square root of negative 4? Well, what is the square root of negative 4? In lower levels of math, we just say that it's undefined, but all that means is we just have to define it. So we can write it, well, it's defined here, I guess. It's the number that when you square it gives you negative 4. The problem is it's not on the number line. None of these numbers, when you square them, give you a negative. The negative numbers, when you square them, gives you positives. The positives, when you square them, gives you positive. The only number that doesn't give you a positive when you square it is 0, because 0 squared is 0, which is not positive. So none of those numbers are this number. Well, here's how we deal with this. We just have to realize that the real number line is incomplete. These numbers are not all the numbers. There are, as you can see on my screen, imaginary numbers. So what are imaginary numbers? Well, imaginary numbers are numbers like what we have here. So what you can do is you can rewrite this as 4 times negative 1 and separate this into root 4 and root negative 1. Whereas the root 4 can become 2, the root negative 1 we typically call I. I is an imaginary unit. To solve, we do plus or minus 2i. And get a pair of imaginary numbers. So what is an imaginary unit? An imaginary unit is basically like the imaginary number version of the number 1. So the imaginary unit we define as I, which is the square root of negative 1, or equivalently, I is the number that when you square it gives you negative 1. There are actually 2 numbers, so when you square it gives you negative 1. But what you want to do is you want to think of an imaginary number line where here there's a 0, and here you have I instead of 1. You have 1i, and you have minus I over here. Our number from this equation, 2i, is on this number line. It's right here, 2i, and so is minus 2i. So those two numbers are the solutions to our equation. So what I'm saying is the real number line is not the whole story because it's incomplete. It's obviously incomplete because it doesn't contain these numbers, the numbers that when you square them give you negative 4. So what about this number line? Well, this number line we can write essentially all our imaginary numbers as multiples of I. So an imaginary number is typically some multiple of I. like so. For example, I wrote this as 2 times I, therefore it fits my definition of being an imaginary number. All right, so we have real numbers and imaginary numbers, but there are also numbers that are neither real nor imaginary. You can probably guess from the title of this lesson what they are. Let's say you're solving quadratics and you come, oops, brown please, thank you. And it comes across this equation, x squared minus 2x plus 2 equals 0. This is not such a complicated quadratic. It's pretty friendly, has some nice 2's. Let's solve it. How do you solve it? By completing the square, of course. Subtract 1 from both sides, giving you x squared minus 2x plus 1 equals negative 1, because this on the left is a perfect square. This is the square of x minus 1. And then you can solve by doing a square root, and you get absolute value x minus 1 equals the square root of negative 1, and you get x minus 1 equals plus or minus I, giving us x equals 1 plus or minus I. Like so. What you'll notice is that these solutions are not real because they have i's in them. They're also not imaginary because they have a real number there. They're not a multiple of I. These are neither real nor imaginary, or both, depending on how you want to think about it. These numbers are complex. Complex does not mean complicated. It means real plus imaginary. It's as simple as that. Often written in the form a plus bi. That's why up here for my imaginary I wrote bi for my imaginary number. Real number plus imaginary number. Let's call this z. This is a standard form of a complex number. Generally, when you're answering a question with a complex number, you want to try and write it in this form, standard form, with the real part plus the imaginary part. Like so. Okay, complex numbers can be graphed, but to graph them, you need a real axis and an imaginary axis, like so. We can achieve that with a two-dimensional graph. Here we have a real axis, here we have an imaginary axis. And to find the number a plus bi, you just go a in the real direction and b in the imaginary direction, and you end up here. This would be a plus bi. So complex numbers are inherently two-dimensional, which is one of the reasons why you want to write them in standard form, because you can think of this point as a point with coordinates a comma b. And you see it's two-dimensional because it requires two pieces of information, the real part and the imaginary part. That means that graphing complex valued functions is very difficult. Normally when you graph a function, you have an input x and you put it into your function, you get an output y. So when you graph it, you have two axes, one for the input x and one for the output y. No problemo, but consider if your input is a complex valued function. Notice we sometimes use the variable z instead of x or y to remind ourselves that this is not just a real number. Imagine the inputs and outputs of a function could be complex numbers. For example, you might have y equals x squared, your friendly neighborhood parabola. Oh, that's terrible. One more try. Good enough. Imagine y equals x squared, but who's to say you can't put in a complex number or an imaginary number for x? You could. What if you allow your input variable to be complex valued? That's what I'm talking about. Well, then what you would need is you would need two dimensions for just to plot z and two dimensions to plot w. So to graph this function with its inputs and outputs, you would essentially need 4 dimensions. So things get real tricky real fast, and there's a whole area of math dealing with this sort of thing where basically you do all of math again, but this time you allow all your variables to be complex numbers. And this type of math is called complex analysis. Okay. It was a pretty fun class. Typically, you take this class in college only if you're going to be a math major or something, or maybe a math minor. No one else really bothers with it because, you know, it's hard. Complex analysis is hard because, yeah, I guess you can see immediately why it starts to become hard. Fortunately for you, you do not need to know about complex analysis. My goal now is to show you what exactly you need to know about complex numbers that might show up on the and First thing is how to write them. And And I've kind of illustrated that twice here. So being able to understand that this can be separated like so to write a complex number. So the main idea is if you have a square root of a negative, you separate out the negative part and you write the square root of -1 as I. That's pretty much how you do that. So make sure you comprehend how that works. Here's another example. This one was simpler because I just had the square root of -1, which I just rewrote as I. Okay, but here's what we're going to do. We're going to try operations. So the main types of complex number questions that I see on the exam are about operations, where you have complex numbers, like in this case I made Z and W, and you're supposed to do some calculation with them. Here I have some sample calculations. We're doing operations with complex numbers. An operation is something like plus or minus. Here we're multiplying a complex number by a real number, 3 times Z. Some combo, some multiplying two complex numbers, squaring, dividing them, and so on. So what I want you to do right now is I want you to try and calculate as many of these as you can. What is Z plus W, Z minus W, and so on. I'm going to pause the video and you can start calculating. Go ahead and take maybe 5 minutes or so and see if you can make progress. And when you get real stuck, you can unpause and I'll start to walk through these one at a time. Okay, so Z plus W, you probably figured this out, is Z plus W. And essentially all you're doing here is combining like terms. This becomes 4 for the real part, and the imaginary part is just 1i. So 4 plus I is the answer, and that's written in standard form. So similarly, Z minus W is 3 plus 2i minus, and then note the parentheses 1 minus I, so that I can distribute the minus sign, and I get 3 minus 1 is 2 for the real part, and the imaginary part is plus 3i. And that's the answer to Z minus W. If this gives you a hint for how to do the rest, then feel free to continue practicing. You can pause the video again if you want. Otherwise, I will continue in a few seconds. Okay, so here we have 3z, which is 3 times 3 plus 2i, and we will use the distributive property. 9 plus 6i, that was that. So 5z minus 2w is the same sort of thing. 5z's minus 2w's. And you combine like terms, you distribute, and you do all of the appropriate things appropriately. What is this? 15 plus 10i minus 2 plus 2i, which is 13 plus 12i, probably. I don't know. I'm terrible at mental math. So Z times W is 3 plus 2i times 1 minus I. Again, with the distributive property, this is 3 minus 3i, so I'm going to just distribute, and then distribute this guy as well. Plus 2i minus 2i squared. So that's just, the distributive property or FOIL or whatever you want to call it. Whoops. Your old normal sort of calculation. Make sure you ask questions if you have any. Otherwise, let's continue. Now we want to combine like terms. And here we can combine the negative 3i and the plus 2i. But there's one more thing we want to do. We want to write I squared as -1. Remember, if I is the square root of -1, then I squared is just equal to -1. So I'm going to do that and write this as 3. These two guys can be combined into -i, but then the -2 times -1 becomes +2. So my final answer is 5 minus I. And that's my answer for this part. Make sure you ask clarifying questions if you have them about multiplying numbers. The main idea is this right here. I squared becomes -1. If you can do Z times W, then you can do Z squared, because Z squared is simply Z times Z. So if you write it out, Z squared is 3 plus 2i squared. By the way, if you distribute this power like that and that, you're fired. I'm going to call the math police, because that is a giant no-no. That's not how exponents work. No. squared means times itself, so 3 plus 2i times 3 plus 2i. Let's distribute. This is 9 plus 6i plus 6i plus 3, 4i squared. I got it. I figured it out. Don't worry. Don't panic. And then I squared is -1. So this 4 becomes -4. So we get 9 plus 12i minus 4, which finally combines to 5 plus 12i. And there you go. That's your answer for z squared. As you see, this is kind of a pain. Imagine computing something like z to the 4th. There are easier ways to do this, but they are much more fancy, and I'm not going to teach them to you in this class. Sad face. Okay. Stop and ask questions if you have any. Otherwise, we come to the hard one. Z divided by W. You probably haven't figured this out unless you have seen this problem before. Let's set it up. Okay. So what are you supposed to do? Well, do you cancel the i's? No, that doesn't make any sense. If you do that, you're fired. I will tell you a super secret. Your calculator, if you have something like a TI-84 or something, your calculator can actually do this. If you go and press the Modi button and you go to complex, then there is actually an I button, and you can literally type this in and it'll give you the answer. I don't know if that's cheating, but hey, they're allowed on the SAT, right? But you can't use them in section 3. So if you want to try that, definitely try that. But let's talk about how to do this. So I'm going to show you how to do this by comparing this to a similar problem. The similar problem I want to show you is the problem of rationalizing the denominator of a fraction. So imagine you have 1/√2. This commonly comes out of trigonometry for like a cosine of pi over 4, which we're going to talk about later. Rationalizing the denominator means getting rid of the square root in the denominator. Hopefully you remembered that you can do that with this awesome method of multiplying by 1. You get √2/2. Rationalizing the denominator is called that because now the denominator is rational instead of irrational. Multiplying by 1 is one of my favorite things in math because it shouldn't do anything, and yet it does, which is awesome. Now consider this. How do you rationalize this? I'll give you a hint. It is a similar technique of multiplying by 1. Go ahead and give it a try, see if you can figure it out, and then you may pause the video and discuss for a moment before continuing. Okay. So if you tried something like √2/√2, you'll find that this doesn't work. Because when you do your distributive stuff, this becomes √2 on the top, and on the bottom you get √2 plus 2. So sadly, there's still a square root of 2 in the denominator where this did not rationalize. So that doesn't work. Sometimes I hear people ask if they can square it. Well, there are two reasons why this doesn't work. Reason number one is if you take a fraction, and actually let me take a simpler fraction so you can see what I'm talking about, and you square it, it changes its value. You get a different thing. Squaring changes the value of a number unless the number is equal to 0 or 1. So squaring is not legal because it changes the value of the number. Secondly, you can do an almost squaring by multiplying by 1 plus √2/1 plus √2. See how that's basically like squaring the denominator, multiplying it by itself. But even then, this does not help because on the denominator, you have to, do the distributive property, and you get 1 plus √2 plus √2 plus 2. And you failed to eliminate the roots from the denominator. Okay. The trick, of course, is this, to use the difference of two squares. Imagine, do you remember the difference of squares? A plus b times a minus b equals a squared minus b squared. The difference of two squares is called so because you're subtracting two squares. So essentially when you multiply an a plus b with an a minus b, you get the a squared and you get the b squared separately. There's no ab term. Notice that's what we want. We really want to square that guy. So that's what you do. You multiply top and bottom by not 1 plus root 2, but 1 minus root 2. So that on the denominator, you have the difference of two squares type of action. Take a few seconds and try that right now. Try it on your own while I do it, so you can get the enjoyment. Okay, you should end up with what I have, which I can write as root 2 minus 1. And I think you'll agree, hope you'll agree, that that is much better than what we started with. Yes, it is. Okay, so why was I telling you this story? I was telling you the story about rationalizing the denominator because the way you get rid of a square root is essentially by squaring. And we did this by multiplying top and bottom by 1 minus root 2. This idea has a name, by the way. This is the conjugate. It has an idea because it is frequently employed, very useful tactic. Well, that's how you divide complex numbers. To get rid of an I, you can square it because I squared becomes -1. Therefore, the correct approach is to multiply by the conjugate of the denominator, and you get the difference of two squares action. Pause the video, work this out, and then resume. Okay. Here I go. I'm going to multiply on the top very carefully. So 3 plus 3i plus 2i plus 2i squared over 1 minus I plus I minus I squared. I think I did that right, maybe. This becomes 3 plus 6i minus 2. And on the denominator, we got, that's not 6i. 3 plus 2 is 5i. My spidey sense was tingling. And then you get I squared, which is -1. So you get 1 minus -1, which is 2. And you get 1 plus 5i over 2. You could leave your answer like this, but I'm not going to. I'm going to write it as 1/2 plus 5/2 I. Why? Because this is standard form, A plus BI type of business. Some SAT questions might even tell you to write it in the form A plus BI, and that should be no surprise. And again, one of the reasons why I would do that is because you could imagine it as 1/2 in the real direction and 5/2 in the imaginary direction. That's why you might want to separate these numbers like so. It's not a big deal. I mean, obviously that's right too, but this is what I expect you to have to enter on the SAT. All right, that's how we divide. Take a moment to ask questions if you have any. And that's the end of operations with complex numbers. I will give you this theorem as a bonus theorem. Complex roots of polynomials occur in conjugate pairs. A conjugate pair is a pair of complex conjugates. That was stupid. I don't know why I said that. But for example, this is a conjugate pair. Remember, I used the idea of the name conjugate earlier. Let me formalize that up here, where I define a complex number. Here I have a complex number z equals a plus bi. Its complex conjugate would be a minus bi. And like I said, this has a name conjugate, but it also has a notation. It's z with a little bar on top. And this is the conjugate. You won't see this notation on the SAT. I don't think. They don't assume that level of knowledge, but it's nice. All right. So this is a conjugate pair. The theorem I just quoted you down below was that complex roots of polynomials, occur in conjugate pairs. That is, when you're solving a polynomial equation, they occur in conjugate pairs. That's exactly what happened here. Here we had a polynomial equation. True, it was only a polynomial degree 2 as a quadratic, but the solutions were complex numbers and they occur in a conjugate pair. 1 plus I and 1 minus I. See how the difference is the sign in between, and this is what we call a conjugate pair. So if you're solving a polynomial equation, it is impossible for there to be only one complex root, because complex roots always occur in pairs. Imagine you have a cubic function. You might have learned in school that a polynomial degree 3 has 3 solutions. Therefore, there are either all 3 are real, or 1 is real and 2 complex. That's true, because they occur in pairs. At the very end of our lesson, I have included 2 little examples of problems from the SAT. Go ahead and pause the video and give these problems a try. Okay, these are very easy, just add. You'll notice that this is a problem 2 and a problem 3. These are not from the same test. I doubt you'd find these, but it does show you that it's common to find this level of difficulty of complex number question near the beginning of a test. And these are free points because all you have to do is combine like terms. Yippee, yippee, thank you, come again. Number 3. Sum, of course, means add. And I'm going to be Captain Careful doing the steps of success. Nice little organizational columns. Ooh, 6. Ooh, oh yeah, great. They even tell you that I means the square root of -1, but for your purposes, you already know that, and it's just verifying that yes, these are indeed complex numbers. All right, that's it.